All right, class, we're gonna get started. So today and Wednesday, we have our final two class periods, and we said, or it says on the syllabus, those are gonna be review. We're gonna do, I guess, two different things on these 2 days. So today, we're going to review more or less everything that we've covered in this class, but through the lens of how do you know that you're doing it correctly? And this shades into questions of ethics. There were a number of questions throughout the semester about how do we know that we're using the right test, that get into questions that are not so much about the math of statistics, but about the ethics of when you use statistics or how you use statistics. You could also think of this as a guide to how not to be fooled by statistics, because it's more likely that you all will be evaluating many more statistics than you are generating statistics. And so along the way today, we'll go through some pitfalls in statistical analysis, how we can understand those based on what we've covered in this class, and how to not be fooled when you see them. And along the way, we'll hit pretty much every topic that we've covered throughout this class. So that'll be today's lecture. We'll finish that up if we need to on Wednesday, but it's likely that we'll finish this today. And then on Wednesday, we'll have a more focused review on the material that's on quiz 7. So that'll be lectures 19, 20, 21, 22, and 23. And at that review, I'll also go over the concepts that you should make sure you didn't forget about from the rest of the semester that are also included in that material. Other announcements, we have homework. The final homework is due. I was going to make it due on Wednesday, but I figured why not Thursday? Give you an extra day. So it's due Thursday at midnight. I understand you probably have a lot of things due Thursday at the end of the day. So if you want to get started sooner or treat it as if the deadline is Wednesday, go ahead. Yeah, and then quiz 7 will be in this room. We have a long period because it is a final exam period, but I'm going to expect the quiz to be about the same length as previous quizzes. So officially, I'm listing it as an hour for that final quiz. If you're working on it a little bit longer, I'm not going to kick you out right away, but officially that last quiz is going to be an hour. All right, any questions on any of this before we get started today? Yeah. It's on the syllabus, it's on the registrar's webpage. I believe it's the 13th. 13th, yeah. And it's at 3:30, is that right? Okay.
Just come in on Wednesday like you have class. Good.
I think we have one extra class. Yeah, I believe we can check after. Yeah, but I have double and triple checked it on the course syllabus. You can also use the registrar webpage to make sure. Yeah, that's all right. Okay, any other questions? Okay. So we're going to use, we're going to review where we've been through this lens of ethics, how you make sure you're doing things correctly. Along the way, I'm going to use, wow, that's not good. I'm going to use quite a few comics from, let's see. Well, we can just do it this way, I guess. I'm going to use quite a few comics from XKCD, like a web comic. Let me see if I can fix the view here for a second. So XKCD is a web comic that often has comics about math and is generally pretty spot on when it comes to how you would actually interpret different things in math and physics. So we are going to, let's see, Crestron, let's go scaled. Let's see if this works. Nope. All right, well, we will just carry on in this view, although it's not ideal. Unless anybody has an idea about what I'm doing here, but we'll just go here. Okay, so XKCD also often has some insightful comics that can introduce some of these ideas. And this is one of my favorites about statistics. So it starts with this, one researcher running into another, jelly beans cause acne. Scientists investigate. And they come back and say, we found no link between jelly beans and acne, right, with to a significance level of 0.05. And they say, that settles that. And then someone says, well, I hear it's only a certain color that causes it. So then they go in and say, we found no link between purple jelly beans and acne to a level of 0.05, right? We found no link between brown jelly beans, pink jelly beans, blue jelly beans, teal jelly beans, salmon jelly beans, and acne. All the way down to here is one out of this 20 or so experiments. We found a link between green jelly beans and acne, p less than 0.05. Now, the joke is this is 1 out of 20 experiments at a significance level of 0.05. And so we would expect to get a result as extreme as as the effect that they observed about 1 in 20 times, right? If we had just by random chance, even if there is in fact no effect. And then what they're saying here, what they're showing here is that then that would be the thing you read about in your news feed the next day, right? Is scientists conclude that green jelly beans are linked to acne with 95% confidence, right? Which is the way that that would be reported. So this is related to a pitfall that you will sometimes see in the use and application of statistics. It shades into something called p-hacking, which we'll discuss as something to watch out for, which is looking for spurious correlations in your data by manipulating the way that you collect or present the results, right? If you see the result of green jelly beans and acne, p of less than 0.05, right, 95% confidence as 1 among 20 results, you probably interpret this differently than if you see it as the headline and it's the only thing that's discussed, right? So this gets into how we present our data needs to reflect what we've actually done statistically, and this is likely some place where we'd want to use ANOVA anyway, right? Because we have multiple comparisons, and that's why we do ANOVA, or we have different corrections in ANOVA in order to avoid this kind of a thing. But an overview, like why this is an issue, is that basically everything that we're doing in statistics, remember from lecture 1, lecture 2, basically everything we're doing is probabilistic, right? So we're always providing an estimate that is based on probability, right? That's why we spent time talking about that in those first couple of lectures. The other side of this is that there's no absolutely correct answer, right? So if you say that, jelly beans do not cause acne to a level of significance of 0.05, and then someone comes around and finds some link between jelly beans and acne later, the fact that event was, the fact that you had your statement about it, your original statement about it was only a probabilistic statement. So a single counter example of that could just be a rare event. It doesn't necessarily falsify the result of your analysis, or doesn't necessarily imply that your result was false. And so that means that there's a little squidginess and misconduct, and intentional or not deception can hide in that squidginess. Right, so any answer that we get is probabilistic, so unexpected events should be expected to occur occasionally, right? If we say something, we take it to a significance level of 1 in 100, still, if you do enough trials, you will see that unexpected event. Another thing to consider here is that we often use statistics to show that something is likely true or not, right? So often we're using statistics in service of some perspective. And so that means that there's often motivation to use those statistics to show something is likely or not, right? Depending on what your perspective is or what your motivation is. And related to this is that there's often a trade-off between what we would call statistical power, which is the ability to detect a real difference, and our guarding against drawing false conclusions. So an example was in control charts, right? This lecture is 21 through 23, most recently. We saw that we often are going to be using 3 sigma control charts, which don't give very many false alarms, right? We had a very, very low chance of seeing a false alarm, falsely detecting that a situation is out of control when it is in fact in control. But it also means that then those control charts are not well powered to detect small errors that are due to real causes. And so we have different ways that we can try to improve that. but there's always this kind of trade-off between statistical power and whether or not we're going to draw false conclusions. And so that means, as the statistician or the person evaluating statistics, if you have to understand something about what the underlying test was actually good at. What does this 0.05 level actually mean? And so all of this can lead to some bad behaviors. This chart, I know you can't read this chart, but this is another comic from XKCD, just giving an estimate, just giving a list of some probability comparisons. There's a 5% chance, we often use a significance level of 5%. So it says that there's about a 5% chance that an NBA team down 20 at halftime will win the game. So it happens, but not necessarily that often. And so this can be just a way of maybe guiding your statistical thinking. So even rare events do happen, and all of our estimates are probabilistic. So I want to start by talking about hypothesis testing. This will be related to that first comic that we saw. So the basic idea, just as a review, and that image comes from lecture 9. So the basic idea is, if the null hypothesis is true, how surprising is the result that we observed? So in lecture 9, we were doing hypothesis testing about the mean. And so we constructed a distribution of what all of the possible means of a given set of n experiments would look like that follows the t distribution. So we use the t statistic. We construct a distribution according to that statistic. And then we ask for what we actually observed, how likely is it to have occurred just because of random chance? Right. So it could be that our null hypothesis is true, and even if we have something that's way out here in one of the tails, it could still happen, right? Unlikely events can still happen. We just want to know what the probability that it actually happens is. And there are a couple of different ways we can do that testing, right? So we can find the critical value of our statistic. In a t-test, it's a critical value of the t-statistic. In this case, shown here as t-statistic for a p of 0.05. Then in that case, we would then compute the t-statistic for the result that we actually observed, and ask if that t-statistic that we actually observed is more extreme or further away from the mean than our critical value. Or we can also just compute a p-value, which corresponds to the area underneath the tail of the distribution. All right, so and then that was when we're talking about sample means, we use the t-distribution, but it's the same basic process for sample proportions, but the underlying distribution is binomial. Or sample variance, but the underlying distribution there was the chi-square distribution. Right, but it was all the same basic approach. Right, that was a theme that ran through many of our lectures. But a pitfall here is something called p-hacking. So this comic here on the right-hand side maybe shows some, interpretations of different p-values that you might see represented places. So, if we have a p-value 0.03 or less, you'll often see that discussed as highly significant. 0.04, 0.049, we would call that significant. 0.05, oh crap, redo calculations. 0.051 and up on the edge of significance, and so on. Or a 0.01 or greater, hey, look at this interesting subgroup analysis. That's where we get into things like that jelly bean case from before. But this kind of thing, like redoing your calculation when you're just on the edge of significance, maybe adding in a few more replicates if you're just on the edge of significance, that falls into this, or doing a subgroup analysis, looking at every possible color of jelly bean to see if you can get something that meets that 0.05 level. Those all fall into this category of what would be called p-hacking. So it occurs when researchers collect or select data for statistical analyses until non-significant results become significant. And there's a lot of literature and a growing recognition that this does happen. We'll look at some data on that. So here's another example down here. We have exam grade versus how loudly students scream. There's some moderate correlation. And we say, oh no, it's not significant. So we need more data, have them try yelling. into the microphone a few more times. So we collect more data points, and now all of a sudden we get something that's significant, right? The p-value is now 0.037, even though it's more or less the exact same underlying data. And yeah, are you sure we're doing slope hypothesis testing, right? The answer is no, definitely not. But this is another example, right? So if you have a value, this is pretty extreme, but imagine you're running some experiment and you get a value of 0.06. You might think, oh, I could just go in and collect another 10 points and maybe knock my significance level down. But that falls into this category of p-hacking. It's something to avoid and something to watch out for. And it definitely does happen. So this is some evidence. So these are it's like a meta-analysis of papers and results in different fields. This is kind of like a meta-analysis, like discussing results from many different fields. But basically let's start here in the middle in psychology. So in papers from psychology, if p-hacking didn't happen, there's a certain distribution of p-values that we would expect to see in the literature. Basically, we'd expect to see a nice smooth line as we increase in p-value. But if p-hacking does occur, then you'd expect there to be an excess of p-values that are just under 0.05. And that's what's observed. When we look at actual statistical data, actual data from published studies, there's just an excess of values just under that 0.05 level. Same is true in biology. You see this little uptick here. That some amount of that is likely p-hacking, people going in and tweaking their results until they get something significant. Economics, there's, again, a bump here that should be a smooth distribution. Instead, there's a nice big healthy bump right there, or unhealthy bump right there, indicating that there was some p-hacking. Now, it doesn't tell us which papers in this group did that, right? We can't really tell from this, just that there's an excess of p-values that are just this side of significant. And so meta-analyses of published data find that this does generally occur, and there's a last week tonight little segment about p-hacking as well. So it's something to watch out for and something to avoid when you're doing your own analyses. Yeah, John Oliver on last week tonight. Yeah, I guess it's a little bit dim up there. So there are some possible solutions to this. Unfortunately, none of them is necessarily perfect. One solution that's often used is to predetermine how many samples you will run and state ahead of time how many samples you will run, right? And what analysis you're going to do and what your criteria are for accepting whether or not something is true. So this is the approach used in clinical trials. So clinical trials are registered ahead of time. So for example, on clinicaltrials.gov, you can see a list of ongoing clinical trials, what their endpoints are, how they're going to be evaluated, and then results must be disclosed. So another thing that could be causing this, or another maybe statistical bad thing, is running a test and not reporting it if your results are not significant, right? So, or maybe, and then running another test and only reporting it if you actually achieve some significance. So one way to try to address that is to, in case where it's really critical, right, to people's life, is to have these tests registered. And so that way, once a clinical trial begins, its results have to be reported. So that way we have negative results in the literature. And so this Data Colada is a blog that talks about like statistical misbehavior. And they talk about this as maybe the one true answer to p-hacking, but it's not perfect. So here's a paper, a relatively recent paper, 2020, that looked now not just at like every paper or a whole bunch of papers in psychology or biology or economics, but just at papers that resulted from clinical trials, so registered clinical trials. And again, they looked at the distribution of, in this case, it was Z values, but it's very much related to the inverse of the p-value, basically. And again, you would expect to see a nice smooth line in this, but the actual data shows a bump. In this case, a bump on the right-hand side. To a higher Z value would be a lower p-value, and that would indicate that there's something going on, right? Doesn't tell us which studies we're doing this, but just that there's something going on. So it's not perfect. So when you see a p-value that's, you know, maybe just this side of significant, it's worth considering if you really do believe in that result. And at the very least, keep in mind that when we say it's significant to a level of 0.05, it's really not that rare that that result could have been caused by random chance. And so you should be looking for other evidence maybe that that thing is true, right? A pattern of evidence is a lot stronger than a single result to a significance level of 0.05 or 0.01. So another solution would be extreme p-values. So this is what's done in physics. So in particle physics, you know, like there's some data up there from the search for the Higgs boson. And when you see that data reported, it will often be reported to a p-value that is, you know, like 0.00006%, right? So just an absolutely tiny p-value, right? We've been talking about 0.05 most of the time, or 5%. This is far higher, far more stringent level. You know, so indicating, you know, what is the percent chance? It should be chance that the signal is random fluctuation. This would, and this is okay when we're doing particle physics. We have a reactor that's, or a system that's running online continuously for years, generating data. I think this site here has a nice animated version of this plot showing how the significance was achieved by essentially just continuously running this experiment over and over and over again until this little tiny bump here, which is what indicates the potential mass of that Higgs boson becomes statistically significant, and you know, where there's such a tiny chance that that is due to random fluctuation, that it was then taken as discovered. The downside is that this would be overkill or prohibitively expensive for studies in many other domains. Right, so the reason why 0.05 is often what we use when we're studying people, or we're doing you know, some kind of other expensive experiment, is that we just can't collect enough data to ever achieve this level of statistical significance. But it's again somewhat domain and experiment type specific. The downside to all of this, downside here, is that this level of significance, here's a paper arguing that this level of significance may not be enough for even very rare events in physics. So this is for the Higgs search, they're saying that the number of sigma required in order to actually declare that Higgs was discovered, the Higgs particle was discovered, would be 5. But for, you know, some of the others, like gravitational waves, right, which is actually something that has been observed in just the past several years, but for the identification, the positive identification of gravitational waves, we would need something like 7 sigma in order to actually have confidence in that event occurring within the data. So yeah, extreme p-values can help, but sometimes you have to get a little more extreme. So the other thing to keep in mind here is that sometimes if we're doing multiple comparisons, ANOVA is actually what's appropriate instead of the paired comparisons, right? So in the example of jelly beans and the color of jelly beans being linked to acne, what was really being done there were multiple pairwise comparisons of, I mean, it's a comic, so it wasn't really done, but what they're talking about being done there would be multiple pairwise comparisons between, you know, rate of acne or something within different test groups relative to control, and all of those individual tests were tested individually, right? So with multiple pairwise comparisons. But if that were real data and we really wanted to understand what was going on, a more appropriate way of doing that would be to use ANOVA, where we ask the question, is the variance between groups larger than the variance within the groups? And there, it's very likely that you know, you wouldn't have fallen into this pitfall and found one that you could kind of cherry pick and select. So yeah, multiple paired comparisons are another bad way to inflate statistical significance, right? So it's another way that you can inflate statistical significance. So, and then remember, we saw once we had done ANOVA, we did find that there was one group that was likely to be more different from, or an outlier relative to the overall variance within the system, then that's when we started doing what we call post hoc testing, like Tukey or the Bonferroni correction, which you're probably tired of seeing on quizzes, but you saw a few times, where actually in the Bonferroni correction, it was more or less explicit that one of the numbers that you had to compute in the Bonferroni correction is what is the corrected level of statistical significance when you're doing multiple comparisons that allows you to take care of the overconfidence of doing the corrections in a pairwise one-by-one fashion. And if you recall from the lectures, homeworks, or quizzes, that correction was often fairly significant, right? So we'd go from a 0.05 level, we use a 0.05 level of significance down to 0.001 or something, depending on the number of samples that we had. Here again is a question that actually came up during lecture was, how do you know which one to use, Tukey or Bonferroni? And guidance varies. The maybe most honest approach is try both and only accept significance if they agree, if they both tell you that it is actually significant, that one group is actually significant. This is probably not done that often. Most likely people just choose one or the other. But at the very least, just from the outset, saying that you're going to be using one or the other, or following some guidelines from your field, maybe guidelines at the company where you're working, or guidelines that were pre-baked in for the type of process that you're doing, maybe based on a memo or procedure at wherever you're working, that would be okay. The bad thing to do here would be trying both and accepting which one shows you that you actually have significance, right? That would be phishing, that would be p-hacking, and bring us right back where we were before. So curve fitting is another area that we covered. And we've covered this now quite a few times in quite a few different ways. So we started off with linear regressions, right? Early on, that was lecture 5. We said that we could use linear regressions to help us find the expected value when we have a linear relationship between two variables. We can't really use it to find an optimum, but we could at least find the expected value at a given result. We could also use that to do parameter estimates. So if we want to know the slope of the relationship between two values, we can use linear regression to find that. Lecture 15 was something covered on quiz 6 with more regression. And there we saw how we can sometimes linearize a relationship and then apply linear regression in order to do that same kind of curve fitting. We can also do some forms of nonlinear regression that we covered in lecture 15. And again, we can start asking similar questions about expected values, in that case, optimum if we have a nonlinear result, and parameter estimates. And then finally in lecture 20, which is going to be on quiz 7, that's where this data here in the upper right-hand corner comes from. We saw that we can use, again, in this case, it was surface fitting, but it's the same basic idea. This is the same underlying math. And from that surface fitting, we could do things like ask, what is the optimum that result? So we had estimated response surface for yield based on experiments at the points shown in red, right, that were chosen based on our methods for optimizing our fit to that response surface. And in this case, we were asked to find where the optimum was and be somewhere in the center of that yellow dot at the center there. So that's curve and surface fitting. There are a number of pitfalls here related to overfitting and overextension of your data. So one is, you might think, well, if I'm doing this kind of curve fitting, we talked about R squared as a measure of goodness of fit. It's kind of a catch-all measure of goodness of fit for curve fitting. And so you might say, well, a higher R squared value is always better. And you might recognize that as you add more parameters to your model, you will generally get a better R squared value. A good example would be polynomial fitting. So if you have a number of data points and you try to fit a line to it, if we went back even just to the example a few slides ago of student test scores versus scream loudness in decibels, we had 3 points. A line didn't fit very well, but we could have fit a parabola to this exactly, right? R squared equal to 1. Just because we have a better R squared value doesn't necessarily mean that we did better. And in fact, if we add more and more parameters, no matter how many data points, eventually we'll hit a point where a polynomial will just go through every single one of our data points. We didn't cover methods of how to evaluate that, but generally speaking, you want to make sure that your model definitely doesn't have as many parameters as you have data points, but your model should have as few parameters as possible to explain the general trend within the data. There are other methods, statistical methods to address this and evaluate curve fits relative to one another. One of them, or a common one, is based on the F distribution, which we saw in ANOVA. That same distribution can be used in what's called an F-test in order to evaluate whether or not different fits. The other thing here is be wary of using a curve fit to draw conclusions outside of your test set. This would be what's called extrapolation. So here's one danger. So here's a polynomial fit. And if we extend ourselves outside of the data set, we can see some really kind of crazy results. That's why I'm just going to go back here. When we're plotting this response surface, we actually just plotted that response surface for the range of values that we actually tested. We're not going to go outside of that range of values because we have no information out there and something totally strange could be happening. And so we should not generally use data for what would be called extrapolation outside of the data set. Interpolation, so that's more or less what we're doing here, where we're interpolating between points that we've tested for. That's fair game. That's one of the reasons we do this. But extrapolation outside can be very risky, very fraught. Related to both of these, actually, overfitting and problems like related to extrapolation are smoothing lines in Excel. I don't know how many times I see this on reports. I also, an instructor for senior projects, don't do this. Please don't use that smooth lines function in Excel. It results in all kinds of wonky behaviors that are just completely non-physical. If you must connect the data points, just use straight lines or show an appropriate fit and get rid of the connecting lines between. But smoothing lines in Excel can result in things like, it's actually not even as exaggerated as it often is in Excel. In Excel, sometimes, if you had a data point that's up here, as it's trying to construct the smooth curve to get to that data point, it might go like out and then come back down in order to hit that point, and just basically make up data that doesn't exist. So don't use that function in Excel. I mean, better use Python, I guess, but if you have data and you want to use Excel, don't use that smooth line function. Related to this is about graphical presentation of results. So we've seen this, like we use log scale to help to see relationships that are potentially linearizable, right? And by plotting things on a log scale, it can often be a lot easier to see trends in your data. It can also be useful if you have something like this is fuel energy density in megajoules per kilogram of sugar, coal, fat, gasoline, and uranium. And those results obviously wouldn't fit all in a meaningful way on a linear scale plot. So a log scale plot might be useful when you have that kind of large range in your data. But just be aware, log scale can also hide noise. So depending on the noise that you have in your data set, it might condense that down and make it harder to determine what noise is actually present. It can bring otherwise far values close to each other in a way that can be misleading. So just be aware of that. It can be very useful, but it can also be a little bit misleading. Appropriate data visualization is its own topic. In fact, I work with a group here in School of Computing where their entire lab is about data visualization, and they try to come up with better tools to visualize data to then present it and draw conclusions from it. So it is its own field with its own conferences and publications and experts. A brief introduction to it is this book, How to Lie with Statistics. It's kind of a classic in the field, but talks a lot about kind of misleading visualizations and kind of pitfalls there. So some general rules of thumb from this whole giant field is use the simplest representation possible. So avoid unnecessary colors, text, and lines. So just up here in panel A, this thing on the top left is really hard to read and draw conclusions from. This is a lot more clear, right? All of these colors here actually make it more difficult to see what's going on. This black and white representation or grayscale representation is actually a lot better. Same thing down here. This is from a paper talking about plots in biology papers, but the same thing would apply in many other contexts. A rule of thumb, Edward Tufte is like a guru of data visualization. His quote on this is that data representation should provide the greatest number of ideas in the shortest time using the least amount of ink in the smallest space. So according to his guidelines, you would want to get rid of any line, any bit of ink on the page that is not directly providing information. So down to unnecessary tick marks if they're not going to be used, or if you have too many of them, and that kind of thing. It gets a little bit extreme, but again, one place that I've seen this in lab reports is if you take a plot from Excel, it by default has a lot of unnecessary ink, right? There's a lot of unnecessary lines that don't add anything and just make it look like you don't know how to present your data. So oftentimes, if I'm preparing something in Excel, and I do use Excel sometimes to make some plots really quickly, I'll just delete a whole bunch of different things in Excel and turn off the background and that kind of thing. Related to this is avoiding misleading graphics. So a classic example is the pie chart. Pie chart like this is, and it's actually shown up here as well, but in a pie chart like this, you generally should be using areas to represent the frequency of having different groupings. I know you can't even read this. Let's call them the red, blue, and orange. And so the area of each one of these slices should correspond to the amount of within each group. Areas are very hard to estimate, especially areas of these kind of wedge shapes can be very hard to estimate and really draw quantitative comparisons between. Nonetheless, this kind of representation, like this kind of circular representation of the data, is sometimes useful. So an alternative that I'm actually seeing quite more and more is that something called a donut chart. But the basic idea is that it has constant width. And so we then, the relationship between these things is then represented again, still by area, but it's also represented by length along the outer edge of this circle. So this is a lot more clear in order to draw comparisons between slices. And there are many, many other things. And as I said, there's active research going on here about how to do this. All right, so another one is sampling, right? So we often want to know something about population statistics, right? So for example, we might want to know something about the mean mu, or the population mean mu, or the overall population standard deviation sigma. We saw those definitions, lecture 1, lecture 2. However, we cannot usually measure the entire population, so we estimate these instead with like X bar, our sample mean, or S, our sample standard deviation. Right? Remember, we calculate sample standard deviation slightly differently from population standard deviation. So then we talked about methods of sampling and experiment design to try to maximize our information about what we want to know and minimize cost. And so lecture 7, we talked about the link back to the normal distribution, which often underlies a lot of our data because of what's called the central limit theorem. Or if we add up enough random causes, it doesn't matter what their underlying distribution was, our data will tend towards a normal distribution. And in experiment design, lectures 19, 20, some material that'll be on that quiz 7, what we were talking about there was how to, let's say we have a parameter space. This would be a parameter space with 3 different parameters that we're trying to interrogate experimentally. And this is the so-called Box-Benkin design, which tries to optimize our sampling of that space so that we can do something like fit a surface to it and find what our optimum is. There are, again, though, a number of potential pitfalls in sampling that fall into this area of statistical bias. You've probably heard of many of these things like confirmation bias, selection bias. Selection bias is shown up there in the upper right. So they're at a statistics conference, and the speaker says, "Raise your hand if you're familiar with selection bias." And obviously, it's a statistics conference where everybody raises their hand. So as you can see, it's a term most people know, right? That's just a direct example of selection bias. It's a group where obviously everybody there knows about what this topic is. Right, you get a different answer if you went, downtown Salt Lake or something and just stop random people and ask them. Outlier bias is another one. So we talked about this very early on. So if we have some data set in which there are some notable outliers, or there are outliers that may drag the mean in one direction or another, and a classic example would be salary data, then the mean is actually not a very good indication of the central tendency of that data set. And so the median would be more appropriate, but that you could call this outlier bias. There's observer bias. Whoever it is observing something may have a different perspective than it's necessarily more appropriate. Another interesting one is survivorship bias. So this is data. The classic example here is aircraft. It's like a bomber in World War II. And what's shown in red here are all the points where on bombers that return back to base, where they notice that there was damage to the airplane. And then, the question is, okay, you want to improve the survivability of these aircraft, right? Like, where do you add armor, right? You can't add armor everywhere because you want it to fly and it still has to carry payloads and everything, people. So where do you add armor, right? This is where you observed all the holes in the plane. Should you add armor here? A lot of planes with damage right there. Should you be adding armor right there? I see a no. Why no?
Because you're selecting the planes.
You're selecting the planes that survived. Yeah, so this is a sample. This is selection bias. So this is survivor bias. So this is a sample where these planes survived. So what's not shown here are the planes that didn't make it back, right? And maybe had damage to the engines, right? Or this part of the tail. And so confronted with this kind of data, you'd want to maybe armor the spots where you didn't see the damage, right? So that's survivorship bias. And that's kind of the classic example. So just be aware of these things. So one way of dealing with this is randomization. So randomization is a key element of experimental design that is that can help avoid bias. I showed data. This is data from a set of experiments I ran at one point as a graduate student with a number of different conditions. It was different microchannel sizes shown as different colors, different microchannel sizes, different currents, and different concentration of salt that I was running through the channel. So I had a 3-factor experimental design. But the pitfall that people often run into related to randomization is they'll take, let's say you do your Box-Benkin design. I'm going to go back. So let's say you do your Box-Benkin design, you do the responsible thing, optimize your sampling locations in order to get the best possible range of experimental results. But then you go ahead and you run all 4 of these conditions at once, then all of the conditions in the middle, then all of the conditions down here in some systematic way, right? So you put them in a very non-random order. What you're leaving yourself open to is, maybe over the course of your experiment, let's say you're going generally from this top left corner, this top corner up here, down to this bottom corner. And it may be that over the course of your experiment, things just drifted over time. Your instrument might have drifted out of calibration. The material that you're using may have been slowly expiring, or something else could have been happening over time. You could have been getting sloppier with your results. You could be getting more careful with your results. Something could have been happening to cause different results at the beginning and the end. And then you might falsely attribute some variation, some trend that you see that was caused by something happening over time to what you were actually trying to measure in your result. And so randomization is an important tool that can help us avoid that. In this case, I tried to randomize, I just used a random number generator to come up with my list of conditions and try to avoid. I had groupings that I couldn't do in completely random order, but I at least didn't do this in escalating concentration order, right? So I went 0.1 to 0.05 to 1. And then my currents, those were pretty easy to randomize. So I just did those in completely random order. I think these color blocks indicate like different, or those are just days on which I ran the experiment. But randomization can help explain what's going on. This is one of my results, which is kind of cool and still unexplained. There's a microchannel here, a nanochannel in the middle, a microchannel on the other side, and we run current through it. And then what I'm plotting here is the color indicates the salt concentration, how concentrated or deconcentrated the salt became. And we can see it becomes reduced in concentration on one side, increases in concentration on the other side. This is the whole thing I was trying to study. But there's all these crazy dynamics and stripes that, I mean, I ran this was 15 years ago. I still don't understand why. But at least I had randomized the experiment so that when this occurred, I wasn't falsely attributing it to something else. So another note about randomization is that we have generally implicitly throughout almost everything we've done this semester assumed that the data was collected in a random fashion. So we've stated this a few times. I pulled out some examples. This is from lecture 7 and lecture 17. In lecture 7, we said that to ensure a statistically sound sample, it's essential that the sample be chosen randomly. It means that each unit is chosen at random. The selection of one unit does not affect the selection of the other. And down here in lecture 17, we also said that there had to be a random sample, but in general, for almost every type of analysis that we did, we assumed that the sampling was done randomly. So it's implied in our methods, and that means it should be built into your experiment design wherever and whenever possible. This is another mistake that I've seen in senior projects, where students will come up with a nice list of maybe box Bankin-informed experiment design with a whole number of different conditions, and then proceed to run through them from smallest to largest or whatever it is. You should always try to randomize whenever possible. Okay, next one, I want to talk about our error bars and confidence intervals. So we talked quite a few times, I think this is the last topic that I have for today. So we talked quite a few times about confidence intervals and how to compute confidence intervals on different types of data, right? So we talked about confidence intervals on the mean, confidence intervals on sample proportion, confidence intervals on sample variance. And again, depending on the appropriate underlying distribution, we would use different distributions to compute t-statistic, binomial statistic, or chi-squared statistic. But in the end, we'd come up with we have similar kinds of methods. We also talked about propagation of error, which is another way of developing confidence intervals when we don't know the underlying distribution, or we don't have good statistics on the underlying distribution of our output, but we know a bunch of inputs to the problem, and we understand the physics or chemistry or whatever it is, the governing law that goes from input to output, right? So here's, importance of understanding error propagation is to maybe avoid that fractal pattern, where it says he doesn't know how to propagate error correctly, so he just puts error bars on all his error bars. We want to avoid that, and so we'll propagate error correctly. But a real example of where you might see this prop up, and this isn't so much an issue of maybe people making unethical decisions, but it's just that there are multiple different ways of doing it, and you should be aware of what those mean. There are many different types of error bars that could all potentially be used. So this is showing, this comes from this application note paper down here. So these are error bars for standard deviation, standard error mean, and 95% confidence interval. These are probably the most common types of error bars that you'll see on real data, or that you might use yourself on real data. And these have been drawn so that we have two samples, one with a mean of 0, one with a mean of 1. And then we've drawn error bars that just barely touch. And then ask, what is the level of significance on differences between those two mean values? Right, so what is the level of significance that we could ascribe? And if we have standard deviation error bars that are touching, we actually have a pretty high level of significance for differences between those means. Standard error mean, we end up with a fairly low level of significance, and with 95% confidence interval, we have that. I think it should be 0.05 actually, not 0.005 p-value for difference between those two means. So what this comes down to is you just need to recognize what type of, if you see a plot with error bars, you need to ask yourself, what do those error bars actually mean? And if you're preparing a plot with error bars, you need to think carefully about what error bars you're going to show. So standard deviation, this would show us the distribution of values within the underlying data set. And these tend to be the broadest error bars that you'll ever see, would be our standard deviation error bars. Standard error of the mean, if we're trying to draw some comparison between two different values and the average result from those two different groups or from multiple different groups, then it's often appropriate to use a standard error of the mean. This would be standard deviation, remember, divided by square root of n, the number of samples, right? So these standard error mean bars are always going to be smaller than standard deviation. But it can be appropriate when what we want to talk about is the difference between the mean values. 95% confidence interval, I should have put it in the formulas here on the side, but the 95% confidence interval, this is the standard error mean times the t-statistic value. So these are always going to be bigger than the SEM error bars, and are appropriate if what we're trying to do is show if we can interpret, like, to what level of significance can we interpret a difference between the means of the data. So interchangeably maybe with SEM bars. But just be aware that this is often it should be reported whenever you see error bars on something. Somewhere the author should state, the report, memo, publication, presentation should tell you somewhere what those error bars actually represent. If they don't, just be careful, right? Because seeing these error bars that are just barely touching means totally different things if they're standard deviation or standard error mean. Okay. So these would be entirely different, right? Here I would say these two means are definitely not the same, right? These are standard deviation bars. And here the interpretation would be they're actually, we have no evidence to suggest that they come from different distributions, right? So it can be a little tricky. Guidance on this comes from my PhD advisor, his attempt to simplify things. The main thing I'm showing this for you, the main reason why I'm showing you this is to point out there's a lot of decisions to make. So this is kind of a decision tree to ask the question of what kinds of error bars or range bars should I be showing on my data, just to give some guidance among those different types of error bars that you might use. And included in here is something we didn't talk about, which was if you have a non-Gaussian distribution underlying your data set, what would you use? If you know what the underlying probability distribution is because you're talking about variance or proportion, then you can actually directly compute the range bars. If you have an unknown distribution, there's actually another estimate that you can use. Propagation of error is actually in here as well, which we covered earlier in the semester. But the point is that there's a lot of decision making to be done that goes into deciding which type of error bar you're going to show, and just don't be misled when you see error bars. They can mean different things depending on how they are presented. So in summary, and I'm use this overuse thing here down here, but using statistics ethically, using them appropriately, interpreting them correctly, it's a key responsibility of yours as an engineer, right? So as you're going to go out and work, even as you're doing an internship, right? You may find some situation like this, hopefully not, but where big boss person says, this is what I want to say, see if you can find some statistics to prove it, right? That might lend itself towards p-hacking or some other kind of bad behavior. So this comes from AICHE Code of Ethics. It says members shall issue statements or present information only in an objective and truthful manner. And definitely some of the things that we talked about today on problems with statistics definitely would go against this this policy. And so we've talked about a lot of different things in this class about how to do different types of statistical analysis. But one thing I want you to take away from this is that, again, because all of our estimates are probabilistic, there is not necessarily any one given answer, and you will often be using statistics to motivate some points. There are decisions to be made in how you do those calculations and present those results, and just make sure, right, you now have the power to do this, make sure you're using that power responsibly. And keep this in mind as you're evaluating statistics. So with that said, that's where I want to end the lecture for today. Any questions on this?